is here, just across the lobby as well. Lunch is 12 to 1 every day. So we have a varied program. Most days are quite mixed, with the exception of Wednesday and Thursday. So Wednesday we have Introduction to Applied Scientific Machine Learning with Mr. Chris Rakaukas, and he also took over a session from Mr. Anas, who could not travel last minute because of health reasons. So Wednesday ended up as Chris Day, and Thursday we have ocean modeling, organized by Mr. Gail Forget. Thank you for that. I realize you're not seeing my screen, but it is. I'm basically following the program. So, in regards to the program, there is one thing. You'll notice that every day finishes what we call the expert hour, for lack of a better name. It's 1 hour, 4 to 5, and the purpose of this is to do informal but kind of possibly more organized networking. So the goal is we all stay here, and if we have questions that came up during the day, or if we have some work problem or some issue, some doubt, some question to any of the people present, we just go to them and ask. Sometimes they might take over the podium and present some stuff for everyone, or they might just talk with you individually. It's totally up to the intervenients. So I don't need to say this, but we're all here not to play nice. Questions are welcome. Normally we will prefer at the end of the session, specifically on the delivery sessions. Of course, during the hands-on sessions, there are a few of those. Then the dynamic is the hands-on dynamic, as always. So I think that's that in terms of logistics. We could probably start with the first presentation. So my name is João Pinelo. I'm the head of data science, cloud infrastructure, and development at the Air Center. Maybe we could turn off these lights here, or. Is this better? No, it's too dark now. Yeah. Okay, so. And I'm going to talk a little bit about compute in the reality of the Air Center, in our reality. And this will lead why this full support to Julia, why we like to support Julia, why we like to support communities, why we do that, and why Julia specifically, and specifically for Earth observation, which is most of our work. So when we talk about computation, we often talk as if it was abstract, as if it existed outside geography, energy systems, outside politics, and outside consequences. But computation is not abstract. It's certainly not abstract for us. It's certainly not abstract in the contexts we operate. It is physical, it consumes energy, it occupies space, it depends on networks, and it inherits the constraints of that world in which it operates. Over the past years, through projects at the Air Center, through the Atlantic Cloud and other initiatives, through work with local communities, we have learned this the hard way. Not as a theoretical exercise, but as a field experiment. We had to build systems that have to work continuously, reliably, and under real limitations. So those limitations are not bugs. They really are the design space. We have to design within that context. So energy availability, latency latency, cost, jurisdiction, environmental impact, these are now first-order variables, and they're not afterthoughts anymore. So the question is no longer how to compute more, but how to design compute that makes sense in this real world. So today I want to reflect briefly on what we have learned so far, and then look forward and what it means to design computation deliberately, under constraints, and with intent. So talking about 4 main points, constraints, what are what the constraints that we've been facing forced us to learn, what worked, what did not work, and what changes, what happens next. So it's not a success story that I'm going to tell. It's basically more like a field report than anything else. So the Earth Center exists in the international context, and we are part of several international networks like the Marine Biodiversity Network, United Nations Environment Programme, the European Space Agency laboratories, and the European, the RCTS, so the European Network for Scientific Computing. And we also have partners across several continents, spanning all the Atlantic. So you might look at this and think, okay, this looks like there is this is a map of reach, right? You could see it that way. What we actually see after a while is that this is a map of latency, of regulation, of energy variability that becomes super apparent when you try to work with these geographies. So it's not a map of reach, it's a map of constraints, real constraints. And these constraints basically disqualify centralized architectures that we tend to use or become accustomed to. So in the Atlantic, these constraints are impossible to ignore. I mean, the distance matters, connectivity matters, energy matters, all parts of the system matter. So weather matters. And yet this region, it's a peripheral region, and it's treated as so in the global compute architectures, something to connect to rather than something to design from. And based on our reality, we have to adjust this. We have to design for this reality. We have to deliver to this reality. And the Earth Center was created in this context. I mean, it's not as a data or a data center project, but and not as an academic initiative, but as a platform for collaboration. And if it's for collaboration, it has to be reliable, it has to work, and it has to work in these different contexts. So collaboration across geography, across disciplines, across institutions, and many of these face similar constraints. So working from the Azores and across the wider Atlantic, from Europe to Africa, from the Americas to island states, we have to design systems to assume latency, that assume limited resources and that assume long-term operations rather than short-term demonstrations. This is our goal, from short-term demonstrations or prototypes to long-term operational systems. So this is where many of our systems emerged from. It's from this context, from these limitations. The Atlantic Cloud is an example, which is still in its infancy, but it's an initiative that we care very deeply about. The Atlantic IoT Network that started as a IoT network for the city of Angra, the city where we are now. It became the IoT network for the island, then became to the Açores, and now it seems to be expanding through the Atlantic. And a range of other operational services supporting science, communities, and industry. And not as experiments, but infrastructure that has to function under real conditions, under the limitations, the constraints we face. So that Atlantic perspective is not a limitation. It's a forcing function. It makes these trade-offs visible, and these trade-offs, by the way, are increasingly global. So they offer a preview of the constraints that we face in the globally, worldwide, that the world now is beginning to face, like energy limitations. So we always work at the Earth Center aligned with communities and aligned with sustainable development goals. So we want to support local communities, local economies, and for that we make sure we are aligned with the sustainable development goals. So now I'm going to go quickly through a few examples of lessons we learned through projects we've done or initiatives we maintain. So supporting a municipality to install photovoltaic panels, they needed to know where there's more sun. Basically, it's a fair enough question, and there's data for that. Copernicus Atmosphere Monitoring Service has that. We went back 10 years, and we made a map for the municipality to make an informed decision. So the output here is that, like, we tend to focus a lot on our work, right? Our data sets and stuff, but the real world cares about the impact, cares about the information that comes out of that, right? So just a call here for this. So local energy production mattered much more than the time series that we use to do that. That's just the data. What the real world wants is always, of course, information. This is support livestock producers, an alert system that's been operational now for maybe 4 years or so. And the lesson here is mostly that prediction accuracy was secondary to trust, to uptime, and to explainability. And the explainability is super important for this specific. It was very important for this specific project because we started the project based on the existing scientific knowledge, and we came to challenge that, and we made progress there too. The project helped science make some progress as well. In another one, where support farmers take care of the health of vineyards, seasonal reliability mattered more than model sophistication. What again matters is that we can deliver information. So a harder lesson was when we moved on to a project where we actually developed hardware, and we come to realize that we did solve the technical problem, but we didn't solve the adoption problem. So for that delivery, you probably need another round of funding to be able to have the system that works, bring it to fruition. Right? So in hardware and operational systems, funding the build is not enough. We need to look way beyond that. The tricky part, of course, is how do you get enough funding to also get things out there before proving that they work. But it's not a technology of failure, it's a failure of how we fund hardware-based compute. So another project or initiative we have, Adriana is going to talk more about this later, it's supporting scientists and the industry. Global monitoring of internal waves in near real time, and this is a global initiative. We're monitoring across the globe in near real time. Oh, and here again, I mean, continuous operation was the lesson. That matters more than peak accuracy of the model. So in the age of AI, because AI seems to have taken over compute seems to now be similar or synonymous to nearly to compute. All of this collapses if compute cannot be operated, like delivery to users. So the applications stop working if we can't compute. We cannot simulate. We cannot do data analysis. We cannot do AI. So we, in order to address the need for resilience, but to address the differences that we find across the Atlantic, we started the Atlantic Cloud, which is basically shared infrastructure. It's a series of nodes working together across the Atlantic, different compute nodes. So it's not about scale, of course, it's about placement. And we need to do this because hyperscalers could not give us predictable latency, they couldn't give us jurisdictional clarity or operational sovereignty, and cost stability. So it's not about a centralized infrastructure at all, it's about a coordination layer, basically between us, Air Center, and all our partners across the Atlantic. So the Atlantic IoT network, as I mentioned, started here, but it seems to be growing, and it grows for, it's low cost, it's low bandwidth, it's low power, so it takes less assumptions, it takes less for granted. So it's designed for environments where power and bandwidth are assumptions and not guarantees. So this brings us to compute efficiency, right? So compute efficiency, we have at least 3 layers. We have the software layer, the hardware layer, and then the system level efficiency. And we think that this is the problem. I mean, this is the bottleneck now. This is what we have to address. In terms of software efficiency, we are, of course, concerned, and we have to keep improving. In particular, not that software isn't great, it's just that in many instances we're using all software that could be more efficient if it was rewritten or some parallelized, etc. Hardware efficiency, it's a matter of power density now. Power density increased by tenfold in the last 10 years. But system level efficiency, so the useful compute divided by the cost of the operational cost of operations, the total cost of operations. So the efficiency gains come from architecture and placement. So the system, what we're calling here system, not just raw power. So in terms of computing efficiency in software, we tend to use highly performant languages, and of course that's why we support Julia so much. It's the 4th edition here of the JuliaEO. I mean, these matters, all of you make a difference here. Like, all your work will have a huge impact when you stack up years and years of operations of your software, when it becomes operational. It's hard to ignore the power efficiency of GPUs. You could argue that a lot of computation should transit from CPU-based to be GPU-based, because the price per core, both of building and maintaining, operating, is way, way lower. And then green compute has been largely seen as a data center problem. But if you can't operate in data centers for the reasons we mentioned, then how do you solve that problem? So you have to think about it as a system problem, and we have to bring all the components to the fore. Data centers, by the way, they use up to 40% of their energy just for cooling, so not even the essential thing they have to do, which is to process and store data. They consume 2% of global electricity usage. And they consume more energy than overall data centers in the world, more energy than many countries. So what we have found at the Air Center is that energy is really, the availability of energy is a limitation. And the world is facing that now because of AI, because of the use of GPUs. We've been learning that in the last few years too. Singapore has 70 data centers for the Asia-Pacific area, and the demand on land and energy was so intense that had a moratorium to data centers in 2019. So they said, well, no more land, no more energy for data centers, that's enough. And this lack of energy is creating things that we might not all agree with. Microsoft is reactivating nuclear power to power AI and AI data centers. Amazon, Google, and OpenAI are investing in nuclear power. And in the current, the amount of energy required for the data centers dedicated to AI that are currently being built is around 600 terawatts per year, which is double what Brazil consumes. The whole Brazil with 300 million inhabitants consumes every year. So another issue about compute, the traditional compute in data centers, the hyperscalers, is fresh water consumption. So they use a lot of water. In 2014 alone, the amount of water used in the data centers in the US alone was enough to cover the area of Germany and Poland together with 10 centimeters of water. And finally, one last example. I promise to move on. If we were to not have used energy for cooling, so not all countries report energy used by data centers, etc., but Germany did a really good report of this. They did report for a few years, consecutive years. If Germany had not used cooling for the data centers, if the data centers were more efficient, then they could have run 5 extra years without the same energy. And it turns out this might not be impossible. So AI power growth is directly tied to the moratorium in Singapore, nuclear reactivation, grid stress, not to mention prices and availability. So energy is no longer the cost, not just a line of cost on the budget, it's actually a hard limit. We hit a brick wall in that sense. So the Air Center is supporting or has a spin-off called At Depth, which aims to do sovereign underwater edge clouds. So high density, energy efficient, private AI compute deployed in ports. AI or HPC, in terms of setup, it's irrelevant, but zero energy for cooling, so 40% less energy or 40% more compute, any way you want to put it. So the vision is a world where cutting-edge computing power and environmental sustainability coexist. We showed it's possible. We exist because of the current cloud model that does not resolve the constraints of field at the Air Center, and we believe the new private clouds will require. We're not an hyperscaler. We don't want to be the cheapest compute, and the goal is not general purpose public cloud. Power density has increased a lot, and we can have now in one machine more power than we can cool if we cool through the traditional methods. If we place the load underwater, we can cool this passively. So the problem is no longer powering racks, it's where the racks are allowed to exist, where you have availability of energy, feasibility of cooling, where you don't rely on water, so water scarcity, it doesn't matter, and urban deployment limits. So we design for density and locality and long-term operation. We proved that we can have passive cooling, no thermal throttling, no not a lot of pressure on the hardware because of the because there are no temperature spikes, so much more constant operations, and the cost is not higher. So we believe the future of compute is not abstract, it's local, it's constrained, and it is intentional. Languages like Julia or systems and architectures that respect this will matter, will be on the map, and the rest will not. So to conclude, I mean, over the past few years, we have learned that computation does not fail where benchmarks fail. It fails where systems meet reality, where we deploy in a different reality. For example, we cannot have a system that is that works in Paris deployed in the coast of Nigeria, for example. So energy is intermittent in many places. Latency is unavoidable. We have to think about funding deployment and operation, not just funding deployments. And we have to create an infrastructure that can be adopted, can be used. And so for us, at least, these are not edge cases. These are the conditions under which we operate. And most of the world is becoming to realize that some of these limitations actually are global, so like the lack of available energy. So what this means is that the future of compute will not be decided solely by faster chips or larger models. It will be decided by where computation is allowed to exist and how long it can operate, and crucially, how it can be trusted. Who trusts that infrastructure and those models? So the shift, that implies a shift in the problem or in the way to perceive the problem from performance to placement. We believe placement is crucial, and regulation, NIS2-driven regulation, is a major fact of that. So it's not about squeezing more flops from silicon, it's about designing systems that respect physics, geography, energy, and institutions. Systems that can run continuously, not just prototypes. So languages like Julia are a crucial part of the puzzle, and that's why we support Julia. And as you're going to see next, we're trying to port some existing loads to Julia, and continue to organize this event. So we started a little late. So this is the end of my presentation. We started a little late, but we left a lot of gaps during the morning because first day can always be tricky. We have a new presentation now. If you're ready, Amit, you're okay? Just introduce.
So it's Amit Ruhela.
Yes.
Good morning, everyone. Welcome to JuliaEO conference. It's great to see so many technocrats, leaders, and change makers gathered in one place today. This conference is about learning from real experiences, meaningful conversations, and insights that help us grow in business and in life. To begin today's session, it's my pleasure to introduce our first speaker, Amit Ruhela. Dr. Amit Ruhela, the HPC group, joined HPC group at TACC in January 2020. Before TACC, he was working in the network-based computing laboratory at the Ohio State University. He has more than 17 years of R&D experience in HPC, social computing, and telecommunication. He is currently working on novel designs and algorithms in parallel communication to deliver the best performance and scalability for scientific and engineering applications. He has also conducted large scalability studies and performance evaluation of HPC applications on leading supercomputers. Dr. Ruhela received his PhD degree from IIT Delhi and VITEC degree from NIT Kurukshetra, both in computer science. He has worked closely with researchers from the Ohio State University, NICTA Australia, IIT-D, C. Delhi. He has also worked with computational scientists and researchers from TACC, SDSC, OSC, UMH, LLNS, University of Oregon, NCAR, EPFL on NSF and XSEDE proposals. So I would like to welcome Amit Ruhela.
Thank you for the introduction. My name is Amit Ruhela and I'm a research associate and manager at TAC, Texas Advanced Computing Center in Austin, Texas. And today I'm going to present our benchmarking for tax systems as well as my experiences with Julia so far. This presentation is basically three parts. First, I would say about the systems that we have at TAC. And second, we'll look at the benchmarking methodology that we are going to use or we'll be using in our upcoming systems. And third, some of my experiences with Julia. So regarding TAC, TAC is a small center. It's almost like 200 employees working at TAC, basically on high performance computing systems. And we deliver some of the nation's large scale HPC centers. TAC is young, it's like 25 years old. We started in 2001, 190 staffs including 70 PhDs. We operate some of the largest systems like Frontera, which is going to expire this year, but still the largest in US academia. Then we have Stampede 3, Lone Star 6, Vista, Jetstream, and Chameleon. In total, we have 12,000 nodes, 1 million cores, 1,000 GPUs. And we support around 3,000 projects for 40,000 users every year. These are our systems as of now. The latest system is the Vista machine, which is AI-centric machine. And we have a continuous need to build the newer systems, particularly the demand comes from the changing hardware architectures, the new workload requirements. For example, AI is at boom now. Everyone wants to do AI whether they know it or not. And then newer workloads are requesting newer type of systems that can deliver the performance they need. These are the systems, some summary of those systems. TAC was primarily the Intel systems. For example, Frontera and Stampede 3 both for large-scale Intel systems, but the shift has moved to AI, and for AI, we have now set up the Vista machine, which is Grace nodes and Grace Hopper nodes. Grace is delivered last year. It has 827 nodes with 576 GPUs. And now we are moving towards the Horizon. So we are moving from Intel to NVIDIA platform. So Horizon will be delivered this year. Some part of the system, at least the Grace Blackwell nodes will be delivered this year, and Vera nodes, which is the CPU systems, will be delivered the next year. So Horizon machine will have 6,000 nodes, 6,752 nodes. The GPU would be NVB200, and we would have 4,000 GPUs. The interconnect for this machine would have a NDR interconnect for CPUs and XDR for GPUs. So before delivering Horizon, we just gave Vista to the nation, and this is a AI machine-centric resource. mostly funded by the NSF, and some part is delivered or funded by the UT Austin AI initiatives. It's a bridge to horizon. People are moving from one domain to another. It's first in the sense of it's our first ARM system and first NVIDIA systems that deliver both CPUs and GPUs. And this machine has 256 Grace nodes. Each CPU has 72 cores. It's a dual CPU node, which means 144 cores. And it delivers 7.1 teraflops of floating point 64 performance. We have a 600 Grace nodes, Grace Hopper nodes, which are basically H100 nodes, and each Grace node have 240 gigabytes of low power DDR5 memory, whereas Grace Hopper contain 120 gigabyte of memory as well as 96 GB of HBM3. So in terms of OS, it's powered by Rocky 9.3 and is connected by the 15 petabytes of vast storage file systems. So looking at the Grace super chip, it's a super chip containing two Grace dies, and each of the chip is connected by the NVLink chip-to-chip 900 Gbps connection. Each chip is connected with the low power memory, and it can deliver 1 terabyte of memory bandwidth for the two CPU subsystems. That's a diagram for Grace Hopper, where there is a one Grace CPU and connected with the Grace Hopper GPUs via the NVLink. And for the TAC systems, we have 120 gigabyte of LPDDR5 memory and 96 GB of GPU memory. Looking at the architecture of TAC Vista machine, on the top we have a core switches, 16 core switches, each connected with the CPU systems and the GPU subsystem. So in a rack of CPU systems, we have 64 nodes connected via 800 Gbps dual line. It's a basically 400 Gbps line. We have a dual line because we don't have any interconnect so far which can deliver 800 Gbps of speed. So each of the top rack shelf switch is connected with the core switches via 800 Gbps, and 64 nodes are there. And this is a 4 racks of CPU systems, and then 19 racks of GPU subsystems. And these subsystems are connected to the storage network via a management switch. So we are now establishing the Horizon machine. TAC doesn't have a space, so we are moving to the Dell campus in Round Rock, Austin, Texas. And the data center is developed by SEBI, and the center has been developed. Now we are installing the racks, and we are also installing the various other system things. So Frontera was 600 megawatt, but Horizon is now moving to 13 megawatt as of now. We started with 9, but with the discussions with Dell, NVIDIA, and other vendors, the energy consumption has increased to currently it's now 13 megawatts of data center. So in total, we will be having 8,368 CPU compute nodes, and this is not correct. Oh, that was the Frontera. But now these are the current pictures which we have taken in September, where the cooling was underground cooling was installed, and then now we have the floor ready. We are getting the racks from Dell as of now, and we will be installing the Blackwell nodes or Grace Blackwell nodes soon. So each rack in the Horizon system will be having it's not NVL 72. We don't need to have 72 GPUs per rack. We can have even lower. We can go just with the NVL 4, where 4 GPUs could be in the one node. And then Horizon GPU racks will have 144 GPUs and will be around, like, each rack would be 215 kilowatts per rack. Whereas the CPU systems will roughly have the same 72 dual socket nodes. The rack power would be 100 kilowatts per rack, and so we will be having 28 GPU racks, 66 CPU racks, in total 128 cabinets for this Horizon machine, consuming 13 megawatt of energy. Now I'll go to the second part of my presentation, how we do the benchmarking for these machines. So when we started with the Frontera, there was a basic set of benchmarks like MPI, IO, Stream, HPL, and some other key applications. And at that point of time, we had a goal of getting that 2 to 3 times performance improvements against the blue water system. So those benchmarks were defined in 2006. Most of them are still relevant but do not scale. Some of them have become obsolete, and we definitely need a newer way of benchmarking the newer machines. Those were the tests that were done for the Frontera machine. Out of like most of the machines, most of the benchmarks were able to give over 2 to 3 times of performance improvement. In total, we get 4.3 at the time of Frontera system. But now we have defined the characteristic scientific applications for benchmarking the newer Horizon machine, and the goal is to find the applications, the actual code, which are basically represent scientific code or workflows. Those are the codes which cannot be solved today, which will require a newer machine, and we need to define a figure of merit. How can we compare the benchmarking performance from the previous machine to the newer machine? And therefore, our goal is to basically get 10 times performance improvement over Frontera. And this is not an easy way of figuring out the figure of merit. And in this figure of merit, we have defined four characteristics. Does the runtime change? Does the runtime change from the previous machine to the newer machine? Can we run it? Can we run it faster? Basically, the strong scaling. Can we keep the problems? Can we change the problem size? Can we run the bigger problems within the same time frame, which is basically weak scaling? Can we use the lesser of the system or high like fewer nodes of the system compared to the previous system, which is basically a throughput? How many instances of the same application can we run over the newer machine? And does the physics change? Can we add more physics? Can we add more dimensions or variables for the same application and run more use cases within the same run? So the performance is multiple of all these 4 factors, basically the time, size of the problem, ensemble, and physics. So in 2021, we started with an open call for all the scientific applications in the United States, and we got 140 applications for evaluation for the newer machine. Right now, we have 20 set of these applications, which we have worked together with the developers and identified. These are the 20 applications which can scale or can prove the performance for over the newer machines. Some of these domains are astronomy, astrophysics, biophysics, CFDs, geodynamics, material science, and others. So in the last 2 or 3 years, we have worked with the developers. I worked with NAMD developers. I worked with PSDNS developers, and we have really run the large test scales over the Vista machine, and we have predicted what kind of performance can we get over a newer machine. So some of these applications, down-selected applications, are AWP Odyssey, Athena K, Changa, Milk, NAMD, PSDNS, CSOL, Vespa, EPW, NGO, and MUST. And these applications have been, these are the projections that we estimate as of now. For example, Earth application, AWP Odyssey by EFANG from San Diego Supercomputing Center, it's projected to have 11.5 performance improvement than the previous Frontera machine. Astrophysics, Athena K by James Strong, it's projected to have 22 times performance improvement. Changa by Tom Quinn, Physics, Milk, which is a lattice QCD for flavor physics. NAMD, which I worked with UIUC developers, it would have at least 10 times performance improvement than PSDNS by PK Yang from Georgia Tech. CSOL, it's by Alice Gabriel from UCSD, 6.3 performance over CPU systems and 2.4 times over GPU systems. So these are the applications which we have seen so far. This EPW is weird in the sense like we think it will give 2400 performance improvement. The reason is once we move from CPU to GPU core, the performance really, like, there was no GPU component for that application before when we ran it on Frontera, but now on GPU they perform really, really good. This is exception. We are going to remove these exceptional cases. We don't want to take our factor 10 times to like impacted by 2400 times performance improvement by EPW. So definitely this will be out of the key applications for benchmarking. Let's take a look at some of the performance results that we have run so far with the Julia on our systems. We are relatively new for Julia. We have installed 1.12.3. I think that's the latest version for Julia, and these are some of the performance numbers which we have measured so far. My background is MPI, message passing interface, which is a communication library for communication between the nodes. And these are some of the benchmarks which we have run. And this is the benchmark OSU micro benchmark, which is developed by DK Panda and his group in Ohio State. And what it does is it sends a message from one node to another node and measure the latency. How much latency do you expect while using MPI communication? This benchmark measures or compares the performance of OpenMPI 5.0.a against Julia 1.12.3. And Julia does, so in this experiment, I'm not using the benchmark which are part of the Julia suite, but it's I'm not using the OpenMPI, which is part of Julia suite. I'm using the OpenMPI, which is the system MPI, and I have configured my Julia in a way that it uses system MPI. And this shows the performance between Julia wrappers as well as the OpenMPI when they build the OSU benchmarks. It's almost the same. There is no impact of wrappers over the system MPI, and the trend is same for all the kind of message size starting from 1 byte to 4 megabyte. However, the bandwidth, we see some differences in the bandwidth benchmarks, and we see that Julia wrappers perform little worse than OpenMPI. I don't know the reason. It might be some tuning issues, or it might be something else which I need to investigate further, but in a sense, both of the MPIs are able to, both of the implementations are able to saturate the network bandwidth, which is 50,000 megabytes per second. The interconnect is 400 Gbps, and so both of them were able to almost saturate, but with some differences, which is good. Then we have a collective benchmarks. Those were the point-to-point. This is a collective benchmarks, and each benchmark is run with 144. This was run on CPU cores, so 144 cores per node, and this is the kind of communication which we see. Again, Julia performs pretty well for collective benchmark. Basically, the broadcast, which basically sends one message to all other ranks over the two nodes. So definitely Julia makes much better communication for the broadcast communication, and this is the reduced case. In this case, I do the reverse. I do see the reverse pattern where at least Julia performs. So this is the line for Julia, which higher is like worse because it's a latency, and OpenMPI does pretty well with the small and large message size, and there is a weird 128 byte message size where Julia abruptly shows high latency. We need to investigate. This could be a system issue or tuning issue. Most of the time, whenever these benchmark or communication libraries are written or delivered over the general public user space, they are not tuned for a particular system. So some tuning is required always to get to avoid these kind of abrupt latency issues. In terms of all-to-all communication, which is more dense communication, we do see both Julia and OpenMPI works pretty well or close to each other. This is this trend is persist for both the small and large message sizes. Last, I ran some of the scaling performance from 1 to 32 nodes of Grace Hopper system, and I measured the all-to-all scaling performance. This in this example, I chose the message size as 64 bytes and each node has 144 cores, which means I'm running this benchmark over 144 ranks to 4,608 ranks from 1 to 32 nodes. And as you can see, as we increase the number of nodes, since it's a dense communication all-to-all, which means O(n) square communication, so doubling the nodes should impact 4 times the latency. And I do see those kind of like 4 to 5, almost like four times performance degrade over 1 to 8 or 1 to 16. But from 16 to 32, it's 1.5 times, not the 4 times performance degradation. But this is expected, and this shows that benchmarks run without any issues on our system. So last, I just want to make some concluding remarks for the experiences that we have on our system. So while using the Julia, there was like seamless installation. There was not even a single issue. Just download, extract, and set up the LD library path and use the Julia. There definitely with the benchmarking which we have run so far, there are some tuning issues which we need to identify, set up the environment variable correctly so that every user can get the same kind of performance or a tuned performance. Our systems are uses the shared setup. We don't want every users to install their own or create their own Julia setup. We provide the Julia module for users, which would have most of the libraries. So we need to identify how do we maintain those versions, how do we maintain for CPU and GPU libraries, which are part of the packages installed within the Julia. So this is a question to me because I'm a system provider and I provide the Julia to our users. So I need to find out like what is the best way, what other centers are doing across the world for Julia, for providing Julia to their users. We have been doing the training for our users. I did one training session last year to our users where I make them learn Julia. And though it's relatively new but much powerful, I feel it's much better than the Python in the sense that it is a single binary. So when you install Python, it's tons of files or millions of files, and each files, when anyone accesses the Python, they generate so much load on the shared file systems. And at least in the case of Julia, that's not the case. It's a single binary, and it's much more file system friendly. Last, I would like to see from some of you are Julia developers or part of the community, so I would like to see some kind of benchmarks, just like ML Commons. If you have ever used ML Commons benchmark, they have a work groups, and under work groups there are benchmarks. So those benchmarks are used by all the researchers in the entire world for AI benchmarking. Do we have such kind of repository, or do we have such kind of mini apps that users can use from the Julia setup? And can you use those benchmarks for large scale performance evaluations or small scale or whatever, the system benchmarking and other performance runs. So I would like to definitely talk with the people sitting here for the benchmarking. So, or can we come up with such a work group which is basically a Julia work group for performance benchmarking over the HPC systems? So that's all from my side. Thanks for attending. If you have any questions, I would be happy to take. Thank you. Yeah.
So I'm very impressed from the numbers you achieved with optimizations of the code. I was saying that I'm very impressed from the performance optimization that you achieved. It's like 22 times, 11 times is like a very good optimization.
Yeah.
Is it because of the work that you did on the code, or is it because you're using a different hardware or more resources?
Hardware is one factor which basically gave you performance improvement, but we have been working with those developers for last 2 years. So we are constantly defining newer ways, like for example, NAMD. I will give you an example of NAMD. So we have got almost 10 times performance improvement. Hardware-wise, if you just compare hardware to hardware, it may be 2 or 3 times performance improvement.
Okay.
But what we have done so far is running the entire code, which was running on CPU to GPUs, and from GPU,
Okay.
like NAMD runs in 2 mode, offload and resident. Like offload, when you can offload some part of the computations to GPU, but resident is like when most of the components goes to the GPU and there is
okay,
less
okay.
CPU-GPU communication.
So there is some CPU
So
to GPU here.
leveraging the
twin
new
times.
GPUs, definitely,
Okay.
hardware improvements, memory bandwidth, number of cores, all these factors accumulate, and then we resolve the bugs as well with like performance bugs. So,
Okay, thank you.
Yep.
Thanks for this great talk. I was wondering when you compared OpenAPI with Julia. So I guess the basic OpenAPI implementation was the same, but
Yes.
once was a C program maybe against or C++, I don't know, against Julia program. Did you had a look at the garbage collector? If this was some issue, maybe did Julia collect allocate some memory, which was not the case for the C program. So maybe this could be some explanation why there is so much difference. Because as far as I know, there should be no intermediate memory allocation when you hand off the things to the MPI library. So maybe that could be one way to check if there is some garbage collector issue.
I would take a look. I don't know about those things. I feel the underlying MPI is the same. When you call benchmark with OpenMPI, and when you call it with Julia is just a wrapper. It's not even like, it's a wrapper around the underlying MPI. So it's using the same MPI in both the cases. So garbage collector, this should not be a case as I feel as of now, because each benchmark is run thousands of time, and every time before the arrays are erased so that the new data comes in. But I will take a look. I don't have any clue about the garbage collection for the Julia. Should I
If I
define it?
might ask a second question, so I'm really fascinated by the by the way that you showed the procurement of the cluster. So there's a lot of things that you can tune, like do I spend more budget on the GPUs or more on the interconnect or more on the disk speed? So how do you reach to this how do you decide how to spend the funds wisely on to have a good compromise between performance,
CPU and GPU.
CPU, GPU, disk, and all this?
So your question is, we were having CPU systems and now we are adding GPU systems. How do we add the newer GPU system? How much?
Or just how do you decide where to allocate more funds? Is it better to have better GPUs or better CPUs or more better interconnect speed?
So I have been at TAG for last 4 years, and every year we have a user group meetings where we ask users like what kind of code they are running, how GPU ready they are. For the last 3 years, none of them say that they need a GPU or they need a very large amount of GPU. TAG provide resources to thousands of applications, and most of the applications, like 98%, above 90%, most of them are not GPU ready. Except if you just leave the AI applications, most of the applications are still trying to adopt GPUs. And that is the reason we are conducting hackathons every year now, for users to come to TAG, work with NVIDIA, work with us, looking at their code, what part can be offloaded to GPUs, and slowly try to run computations in a GPU way. So from the last year and from the AI initiatives by the government and many other UT Austin initiatives, we thought there is a need for now GPU systems, and we allocated part of the system for the GPU. And this is, apart from that, our responsibility doesn't just tie to the GPUs. We also have the CPU systems, like 4,000 CPU nodes as well, for the applications that haven't or they don't need to go to the GPUs. Some of the applications have really scaled well, but most of the applications still needs to adopt the GPU. It's not easy. I think we need to provide resources to both, and it's about the money that we get, like 400 million for setting up this new machine, and we just did like some kind of 60-40 allocations to the CPU and GPU.
Thanks.
Any other question? Okay, thank you.
Thank you, sir. Now, our next speaker is Adriana Ferreira. Huh? Okay. Okay. Sorry, it's a coffee break now, so you can enjoy the coffee. We will be back at 10:45.
Okay, so you need to connect the HDMI cable. Should be here somewhere. Okay, so it's here, so it's just, okay, you don't need this one. Just connect this. And then you start from the first slide. Okay, so go to the first slide. Yeah. Okay, do you have the notes? Notes. It's okay? Yes. Don't forget to click on notes to open the notes. Yeah. Seems like everything is working. You have the